Welcome to the first video of Chapter 8. Chapter 8 is all about exponential and logarithmic functions. Logarithmic functions are new, but exponential functions you have seen before. This first video, we're not really going to graph. We're just going to talk about the basics of exponential functions, and then we're going to look at some applications with compound interest. So let's start with, what is an exponential function? An exponential function is a function of the form y equals a times b to the x minus h plus k. Okay, initially this looks really complicated. What I need you to know is an exponential function is going to have an exponent. X is going to be in the exponent. So for example, we might have y equals 2 to the x. That's exponential. We might have y equals 1/2 to the x minus 3. That x minus 3 just means we're moving the graph a little bit. But these are exponential functions. They grow exponentially. So linear growth is a straight line. Exponential is a curve. Exponential is a curve. There are two different kinds of exponential functions. There's exponential growth, and then there's exponential decay. Okay, so exponential is going to be growing quickly or decaying quickly. Graphically, these are going to look pretty obvious. A graph that is exponential growth is going to be growing. A graph that shows exponential decay is going to be, you guessed it, decaying. It's going to be falling. And this is, of course, as x is going in the positive direction. So as we're going in the positive direction, is our graph going up? Is it growing, or are things getting smaller? So you can see these examples at the bottom of the screen. It says exponential growth or decay. If we look at the first one, as x is going in the positive direction, what's happening? We are decaying. The next one, as x is going in the positive direction, what's happening? We're growing. So these are examples of exponential growth and decay. Now, the reason that these are exponential is they're curves. They're curves. So we also could have linear growth or decay. Linear growth or decay would be a line. So that is something to be aware of. Exponential is going to be growing along a curve, whereas linear will be a line. Okay, now how do we tell if we have an equation and not a graph? Okay, well, let's start with this third example. If we plug in 0 for x, 3/2 to the 0 is just 1. Okay, if we plug in 1, 3/2 to the first is 3/2. If we plug in 2, let's say, 3 squared is 9 and 2 squared is 4. So what we should be seeing is that those numbers are getting bigger. The y values are getting bigger. We have 1, 3/2 is bigger than 1, 9/4 is bigger than 3/2. So this example is actually growth as well. Okay, the last one. Instead of starting with 0, I'm going to start with 2 because of this exponent. If I do 2 minus 2, I get 0. 1/3 to the 0 is 1. If I plug in 3, 3 minus 1 is 1. 1/3 to the first power is 1/3. And let me plug in one more just for fun. If I plug in 4, 4 minus 2 is 2. 1/3 to the second power is 1/9. So in this case, we can see the numbers are going down. They're getting smaller in value. They're not negative, but they're getting smaller in value. This is an example of exponential decay. Now the question is there a way for us to determine exponential growth or decay from an equation without plugging in numbers like we just did? Well, yes, there is. What's most important in the equation is the base. So in the original equation that I wrote, b, whatever's being raised to the power. So in this case, 2 is the base, 1/2 is the base, 3/2 is the base, and 1/3 is the base. Okay, so how do we tell? Well, what we should notice is that 3/2 is bigger than 1, whereas 1/3 is less than 1. So in the case of this example 3, this growth equation, we're multiplying by 3/2 every time. 3/2 to the first, 3/2 to the second, 3/2 to the third. Every time I multiply by 3/2, the numbers are getting bigger. This example though, the next one, that 1/3, if I multiply by 1/3, I get smaller. So if I take a number and multiply by 1/3, it's going to get smaller. Okay, what that tells us, if our base is greater than 1, we have growth, exponential growth. If our base is less than 1, we have exponential decay. Decay. So 3/2 greater than 1 would give us growth. 1/3 is less than 1, that gives us exponential decay. So in the initial examples that we wrote, 2 to the x, if I'm multiplying by 2 every time, that base is bigger than 1, so this would be growth. 1/2 though, multiplying by 1/2 every time, things are going to be getting smaller. That base is less than 1, so this is decay. Okay, you might be asking yourself, what about exactly equal to 1? Well, if we write that example, I'm running out of room, let's say up here, y equals 1 to the x. No matter what x is, I'm always going to get 1. So in this case, y is always 1. It's just a horizontal line. It's not a very interesting problem, or not a very interesting equation. So this is what we got to remember. So first part of this video, we need to be able to determine if both a graph and an equation show exponential growth or decay. Okay, now that we've talked about the generals of exponential functions, we're going to look at a very specific exponential function. It's exponential growth and decay. Okay, so the initial model that I wrote up at the board, or up, not at the board, up top for you, was something like this. Okay, this is not very applicable to us right now. Instead, we're going to write this a little bit differently. Y is going to stay y. So we have P1 plus or minus R over N to the NT. Okay, so initially you're probably thinking these equations are completely different. Well, y stayed y. A became a P. B is all of this stuff. B is all of that. And then we still have the exponent, we're just missing that K. So this equation, the bottom one, is the one that we're going to use in our word problems. We do need to know what each of these variables stand for. Y is the amount after some time. So it might be the amount of money after a certain amount of time, the amount of bacteria in a colony after a certain amount of time. P stands for your principal or starting amount. R is your rate. And N is the number of times per cycle. Oftentimes N is going to be 1. Okay, so we're going to look at some exponential growth and decay word problems. So we're going to set ourselves up an equation and we're going to make some predictions. So let's just look at this example number 1. The first U.S. census was conducted in 1790. At that time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03% annually. Write an equation for the population growth of the U.S. since 1790. Then use your model to predict the population of the U.S. in 2025. Okay, so all of our equations are always going to have an N and a T. So let's figure out what that N and T stands for. It says, write an equation for the population growth of the U.S. since 1790. So we have two variables here, population and year. Population and year. Well, T is going to be time, so T is going to be year. Our Y is going to be the population. Okay, So T, we're not really going to do year. We're going to count the number of years since 1790. So T is going to be the number of years since 1790. Now we have to identify what information we have. Again, we're going off of this equation in red at the top. So P is our principal amount. Do we have that? Do we have a starting amount? Yes, in 1790, the population was 3,929,214. Our R, we're told that we're growing by approximately 2.03%. Now, we cannot use that 2.03. It needs to be expressed as a decimal. So we're going to divide by 100 to change that percent to a decimal. And we get R to be 0.0203. And now we need N. Okay, N is a little bit trickier. What's really important here is this word annually. Annually means once a year. Once a year. So in this case, N is 1. The population is growing once a year or being counted once a year. So like I said above, N is often going to be 1. The only time N is not 1 really is when we're looking at money. So I'm going to give us that note. N equals 1, except when we're talking about money. Okay, so let's set up our equation then. We have Y equals 3,929,214. 1. Our R is 0.0203 divided by 1, and 1 times T. Okay, in the equation, I have a plus and a minus. We're not going to use both. Only one is applicable. We're going to be adding if we're growing, subtracting if we're shrinking. In this case, the population is growing, so we will add. Okay, I want to simplify this a little bit. I want us to put this stuff in parentheses in our calculator, or we can do it in our head just to simplify that a little bit. So we get 3,229,214, 1.0203 to the T. To the T. Okay, so this is our model. Let's make sure that this model makes sense. So this right here is our base. We have a base which is greater than 1, which tells us that this is exponential growth. Does that make sense contextually with what we're talking about? Well, we're talking about the US population. So yes, this makes sense. The US population is going to be growing. Okay, we are not finished with this problem though. We are also told to use the model to predict the population in 2025. So we have to do that as well. 2025, we have to figure out what T is. Well, we need to know the number of years that have passed since 1790. We get 235. So what that tells us is we're going to use our model and plug in 235. So we get 3,929,214 times 1.0203 to the power 235. Okay, you can plug all of this in your calculator. We have to be careful though. This 235 only applies to the base. Does not apply to this 3 million out in front. So make sure that you type that in appropriately. Okay, you should have ended up with a very big number. I get approximately 441935659.7. Okay, initially it's a little confusing to know what this number is. We're going to need to put some commas in so that we can read it. We're going to start at the left. So starting at this decimal point, you go 3 numbers and put a comma. So how do we read this? This is 659. This is 935,000. So this is 441 million. So we are predicting, again, this is prediction. It's not necessarily definitively true. We are predicting the population of the US to be 441,935,659.7 in the year 2025. Just so you know where we're at currently, This year we are at 382 million. 382 million. So I'm not quite sure if we're on track to hit that 400 and almost 42 million. Okay, so that's our first example. Let's look at another example. Please flip the page. Okay, example number 2. A cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from his or her system per hour. Write an equation that represents the amount of caffeine remaining after drinking a cup of tea. Then estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of green tea. Okay, so there's a lot going on. We have to figure out what our variables are. It says write an equation that represents the amount of caffeine remaining after drinking. Okay, so we're going to have our y and we're going to have our t. T is going to be some measurement of time. Earlier in the problem, we see per hour. So t is going to be, the variable t is going to be the number of hours after drinking tea. Y then is going to be the amount of caffeine remaining in the system. Okay, so what do we have here? 35 milligrams is how much we're starting out with. That 12.5% is our R. So we're ready now to write our equation. We get y equals 35 times 1. I'm going to leave that sign for a minute and figure out that later. Now remember, we can't use 12.5%. Can't use 12.5%. Have to change that into a decimal. So we have to, if we divide by 100, move that decimal point over 2, we get 0.125. Now we got to figure out our n. Like I told us, n is most of the time going to be 1 unless we're talking about money. This is not talking about money. And in fact, we see per hour. Per hour means that this happens once an hour. Once an hour. Okay, so our n is 1. Last thing we have to do in this case is we have to decide, are we adding or subtracting? Adding or subtracting? Well, it says that the teen is eliminating, so losing this much caffeine. I'm going to simplify this a little bit by putting this into my calculator. And when I do, I get 0.875 to the t power. Now let's make sure that this makes sense. Is this exponential growth or decay? Well, we look at our base. Our base is less than 1, so this is exponential decay. Should it be exponential decay? Should we have exponential decay? Yes, we should. We are eliminating caffeine from the body, so we should have less caffeine as time goes on. We are not finished. We got to make sure we answer the next part of the question. It says estimate the amount of caffeine 3 hours after drinking. That 3 hours is t. So we're going to do 35 times 0.875 to the third. Now remember that third power is only for the 0.875. It is not for the 35. So you can actually type all this in your calculator exactly how it appears. That's going to be your best option for making sure you get the right answer. Okay, when we do that, we should get about 23.45 milligrams. So again, what I want us to remember is this is a prediction. This is a prediction for the amount of caffeine in this teen's body after 3 hours. It's a prediction. It is not necessarily definitively true. Okay, we have one more to do. This next one's going to be a little bit different because it does talk about money. It's talking about compound interest. Compound interest. So let's read the problem. We'll talk about compound interest and then we'll actually do it. You deposit $500 in an account that earns 3.6% annually. Find the balance after 10 years if the interest is compounded monthly. Okay, before we even try this problem, it's important to me that we understand what compound interest is. So you might have a bank account and that bank account is earning interest. It's either going to be earning compound interest or simple interest. So interest is the money that the bank is paying you to say thank you for keeping your money in the bank. If that interest is compounded, that means that the interest is paid off the principal and all accrued interest. So in other words, if you get interest monthly, the interest that you get will be based on how much is in your account and how much other interest you've gotten. So the more interest you're getting in that account, the more interest you'll be paid. Now, simple interest, on the other hand, this is interest that is paid on the principal only. On the principal only. So if I get interest every month, that doesn't count towards the interest I get in the future. So hopefully we can see compound interest, if we're getting it from a bank, is what we want. When the bank's paying us interest, we want that interest to be based off everything that's in the account, including the previous interest. Okay, I don't know if I explained that well. If not, I can explain it again in class. But that's the difference between compound interest and simple interest. We're going to be looking at compound interest. So let's look at this example. It says you deposit $500. That number's important. 3.6% is also important. It says find the balance after 10 years if the interest is compounded monthly. Compounded monthly. Okay, this is where things get interesting. This is where n is not going to be 1. So n is the number of times per cycle. Well, our cycle is annually, which means a year. So we need to know how many times is this interest being compounded? How many times are we getting paid interest in a year? Well, it says it's being compounded monthly. So in our time unit of 1 year, that means that this interest is paid 12 times. This interest is paid 12 times. Okay, so now we're ready to set up our equation. We know that our principal amount is $500, that our rate is 3.6%, and our time is 10 years. So our y is going to be 500. We have 1. Now remember, 3.6% is not the rate. We can't use that as r. We have to divide by 100, change it to a decimal. We get 0.036 divided by 12, and 12 times 10, because remember it's n times t. Now we have to determine, are we going to be adding or are we going to be subtracting? Well, is our money growing or shrinking? If we're being paid interest, not only do we have that $500, we have the interest that we're being paid as well. So our money is growing. Okay, this can go in the calculator exactly how it appears. My only suggestion would be to simplify that power. Rather than 12 times 10, I would call it 120. So I'm going to pull a calculator up and show us exactly how this would look. Okay, so we're going to type it in exactly how it looks. 500 times 1.036 divided by 12 to the power of 120. There we go, there's our answer. So like I said, it can be typed in exactly how it appears. You just have to remember that 120 only applies to the parentheses, does not apply to the 500. So our answer is $716 and about 28 cents. If we're talking about money, let's round appropriately. So it makes sense to round to dollars and then cents. Okay, so that means if you put in $500 initially in 10 years, you're actually going to have $716.28. Now, initially, you might not think that's a lot, but you haven't done anything. The money's just been sitting there. So you've been earning just by the money sitting in the account. Okay, so this was a quick introduction to exponential growth and decay. Exponential growth and decay are seen all around us. If we think about the number of people who have gotten sick from COVID, that was exponential growth. Not too many in March, but then as time went on, those numbers increased substantially. So that's actually an example of exponential growth that you all have seen recently. So we will be doing more of this exponential growth and decay throughout the rest of the chapter. If you feel that you have understood this material well and that you know what you're doing, you are free to stop the video. If you want to stay on and do one extra example with me, we're going to do that right now. Okay, find the account balance after 20 years. If $100 is placed in an account that pays 1.2% interest compounded twice a month. So let's see what we know. 20 years, that's our time. $100 is our principal. 1.2% is our rate. But remember, we're going to have to divide by 100. So we get 0.012. Only thing we're missing is n. N is not 1 in this case because we're talking about compound interest or money. So we got to figure out what n is. It says compounded twice a month. So we're looking at interest once a year. If it's compounded, though, twice a month, how many times do we get interest in a year? Well, 12 months happens twice a month. So our n is 24. We get paid interest 24 times a year. So now we're ready to use our equation. We have 100, 1, plus, we're adding because our money is growing, 0.012 divided by 24, and then 24 times 20. We can plug this in the calculator exactly how it appears. Like I said, though, I would suggest that you actually multiply those two powers. That way, we're not going to confuse the calculator at all. We're just going to have that single power. When you put this in your calculator, I will tell you, you get about $127.12. If you have any questions from today's video, please make sure you write them down or send me an email or ask in class. Bye-bye.